from the Polytechnic National University, and in my report I would like to present some interesting method for study of free-volume nanostructural in chalcogenide and chalcohalide, germanium, gallium, selenium and sulfur glasses with this second two method. So it is well known that chalcogenide semiconductor are famous materials for preparation different devices for optic and electron memory because they have high transmission in infrared spectral region from visible up to 20-25 micrometer, including two commercial telecommunication windows. But in the last time there are many work concerning thermization and crystallization of these materials for obtaining new practical application in modern photonics. So in this picture we can see our object study for our experiment. We have two parts of the samples. The first one is germanium, gallium, sulfur glasses with some additives of cesium chloride in different concentration, and three based glasses with different amount of germanium and gallium subsystems. And the second one, germanium, gallium, selenium glasses, annihilate during 10, 25, 50, 80 and 100 hours at 380 degrees. This temperature is over than 10 degrees on glass transmitting temperature. So in the result we obtained transmission spectra. This spectra was shifted in a short wavelength region in the case of different amount of cesium chloride compound in these materials, and in the case of so-called cold thermization process, we have different spectrum with different transmission during annihilation of these materials. So in the results, we obtain some interesting X-ray diffraction result for germanium, gallium, selenium glasses with increasing annihilation time from 10 to 25 hours, and after use for 50, 80 and 100 hours, we have crystalline peak near 22 degrees, and this position of this peak is in good agreement with two gallium phases. In addition, in these materials we obtain also the third phase. It's germanium 2, selenium 3, germanium selenium 2 phase. The size of nanocrystalline included in these materials is near 10 nanometer for gallium phases. So, as you see, the concentration of germanium selenium phases in these materials is very short. But as you see in the next slide, this phase mainly localized in the surface of these materials. So it is the base glaze, not annihilate. This sample is annihilate at 25 hours. You can see small formation of this phase. And in the sample annihilate at for 80 hours, we have crystalline phase of these phases. If you have such experiment on crystallization, we have such changes in structure of these materials. And there is a second question. What will be in these materials in their nanovoid structure? In this case, we can use additional method for this characterization: positron annihilation life-type spectroscopy and Doppler broadening annihilation radiation method. So traditionally we can use different methods for study these materials. and we can obtain information about nanostructure in the level from 1 to 100 nanometer. But using this method, we can obtain information about wide structure of materials from 0.1 to 5 nanometer. This method can be used in nanodefect subsystem and in defect subsystem also. So, this is experimental setup for positron annihilation lifetime spectroscopy. In our experiment, we used spectrometer or tag, with whereas source used isotope thorium-22, placed between two identical samples, and then we have some electronical system result obtained as dependence of coincident count from time in computer. So this is what is the physics of this measurement setup. We have isotope. In the result of beta plus decay, we obtained one gamma ray with energy 1.27 mega electron volt. The formation of this gamma ray corresponds to formation positron in the bulk of the materials. This is the start signal. Then positron diffused in materials, thermalized energy and trapped of some voids, and then annihilate onto gamma ray with energy 0.511 and different between two events named as lifetime positron in defects in void. So, in the results we obtain spectra with then trapped mathematical treatment on third component. The first of our one in theoretical work related to the decay of parapositronium, the second one related to the decay of free positrons with electrons, and the third associated with orthopositronium decay. In our materials, in some parts, we have only two components, first and two. It depends of specific of materials and size of void in these materials. So, we have two processes, positron trapping and positronium, orthopositronium, parapositronium decay. For positron trapping, in defect, we can void with smaller size, and in the case of annihilate of orthopositronium, we must to have pores with large size. Because annihilation is process which can be mainly on materials with absorbed water. For these materials, we proposed a model which include two independent canals. The first canal consists of components with intensity E1 and lifetime of this component tau1, and the second one with intensity E2 and tau2. And the third component connected with only positronium decay in materials in part of orthopositronium because annihilation in materials. The first component is no direct physical mining. It's only compensation component. The second one, direct physical mining, and reflects different changes in free volume and in defect in the body. And the third component, in our case, is not interesting for us because we have only analyzed the second component of the spectrum. So, calculate some parameters using lifetime and intensity of this second component. We have average lifetime in the materials, lifetime in the bulk materials, and positron trapping rate in defect. In addition, we have obtained some additional parameters, but in our case will be some interesting intensity E2, lifetime tau2, and positron rate in defect. So our result. In this case, we can see result for germanium, gallium, selenium system analyzed during different time. So we can see that in the initial stage of the process, the lifetime tau2 increase and intensity E2 decrease. Positron trapping rate in defect increase also. You can see in this picture three main parameters for interpretation, evolution of free volume in different solids. After annihilate at 50, 80 and 100 hours, we have inverse process. Tau2 decrease, intensity increase, and positron trapping rate in defect decrease also. So, in the first stage of this process, we have so-called fragmentation process, free volume defect in the body. During long treatment, we have inverse process named as fragmentation. So in this picture you can see this process, agglomeration and fragmentation. Agglomeration reflects different void with big size but small concentration, and during fragmentation we have different small voids and bigger the concentration. In addition to evolution in free volume, we have evolution in formation nanocrystal. Like to this work, in our work, we have nucleation in the initial stage of aniline from 10 hours to 25 hours. In the next step we have formation of nanocrystal of 3 phases. In the case of germanium gallium sulfur with different amount of cesium chloride, we have only fragmentation, agglomeration, dependence of this parameter like in previous cases. And in the case of cesium chloride 15, we have maybe fragmentation, but there is some question in these cases. So in the case of different base glass system with different amount of germanium and gallium of this system, we have also increase of lifetime of the second component and decrease of intensity of this component. Lifetime of this component reflects size of this free volume, and intensity reflects quantity or concentration of defect in these materials. In addition to positron annihilation lifetime method, we use Doppler broadening of annihilation radiation. In this case, we analyze annihilation line with maximum 511. And for treatment of this result, we used fitting process, and in the next step we analyzed S and V parameters. S parameter is defined as a ratio of counts in the central part of the total area to the annihilation line, characterize the annihilation of positrons with low momentum valence electron, and V or W parameters, defined as a ratio of count in the wing part to the total area of annihilation line corresponding to annihilation of positrons with high momentum or electrons. So our result, we made this investigation two places, and our result is near-linear. In this part, we can see near to bulk state. In this part, we have more defective structure. What does it mean? Abnormal and normal tendency in Cauda-Rho correlation. It's dependence between positron rate in defect and density of these materials. At a normal tendency, we have increase of lifetime of the second component and decrease intensity of the second component. In this case, density is decreased also. This tendency is correlated with positron annihilation lifetime data and reflect void agglomeration in this case. In next line we can see fragmentation, which reflects as abnormal tendency. This method can be used only in comparison with positron annihilation lifetime, because this method is not can be used only as one method for characterize the evolution of free volume in different solids. So in this case we can see these dependencies for different systems. In this case we also have normal tendency corresponding to agglomeration process, and in the case of one sample Cesium chloride 15 we have abnormal tendency. It can be connected with some adsorption process in these materials during sintering, during preparation. And there is abnormal tendency for gallium and germanium subsystem that reflect increase of lifetime of the second component and decrease of the intensity in comparison with density, which can reflect a decrease in this dependence. So summarize, I would like to say that this method of positron annihilation can be used not only for characterizing different bulk materials. They methods can be used for study a different system with embedded nanoparticle. We used this method for characterized CO2 nanoparticle embedded to the body, and we obtained some interesting result because we can obtain information on bulk surrounding of these materials in nanovoid performance and nanovoid surrounding formed by this nanoparticle embedded to the materials. Finally, I would like to say thank you for Organizers for possibility to present my scientific work, and thank you very much.
Thank you very much, Halyna, for the talk. So we have time for a brief question.
My question is about your experiment with positron annihilation. Please tell me, what parameter can you extract from this experiment about your structure? As I understood, you try to characterize your chalcohalide object materials with this method. What parameter can you get? It is size of voids, or it is density of states in material or energy?
Okay, well, thank you for your question. It's a very interesting question. So, after this experiment, we have three components: 1, 2, and 3. And we work, in this case, for these materials, only with 2 components. Lifetime of this component reflects size of this nanovoid. we can calculate radius using tau L2 model, and the size of this nanovoid near 0.1, 0.3 nanometer. Intensity E2 reflects concentration of this defect. In addition, friction also in this case no, but in some cases in which intensity of the set component change mostly, we can obtain some information from frequency of this component. This is a parameter obtained from treatment. Positron trapping models, these parameters we calculate from these parameters. And interesting for us, positron rate in defect reflect how many nanovoid is present in the materials, and how you can annihilate in these materials also. In the case of different materials, embedded nanoparticle, we used 3-component fitting. Then we transformed 3-component on 2-component, and from this component we obtain information about also from surrounding nanovoid surrounding in bulk and in surrounding in.
Did you compare these results with maybe other data?
Yes.
With what data?
Yes, I compared this result with, as I say, with CO2 nanoparticle embedded to the body. We was experiment bulk CO2, and then in this materials was embedded nanoparticle CO2.
Only one or several?
Several.
Many.
Okay.
In this case, we cannot to do this because we have different process. We have crystallization with different crystals. It's not embedded nanoparticle.
Okay. Very last question. And brief, please.
What kind of another measurement technique it is possible to use to obtain such information about defects?
About this defect, about this nanopores or nanovoids can be obtained using different porosimetry methods. But as you know, this method can give information about pores or voids from 2. I think that from 2 to 100,000 nanometer. Yes. In this case, we obtain information about nanovoid from 0.1 to 5 nanometer. It's additional instrument to obtain full information about different process in nanoscale level in materials.
Can you also investigate the macropores, the large pores, or only nano?